Okay. Good morning, everyone. It's a pleasure to be here today to discuss the evolution of epidemic modeling, a field that has significantly advanced our understanding of how diseases spread. The origins of epidemic modeling can be traced back to the 18th century with the pioneering work of Daniel Bennell, who modeled the impact of smallpox inoculation. His work laid the foundation for considering how interventions could reduce the burden of infectious diseases on the population. So, as we moved into the early 20th century, the field began to gain more structure, particularly with the contributions of Ronald Ross, who developed models for malaria transmission. Ross' work was crucial in highlighting the roles of vectors and the importance of understanding disease dynamics in population. In 1927, Kermack and McKendrick introduced the foundational susceptible, infected, and recovered model, which has since become a cornerstone in epidemic modeling. This model provided a framework to understand the basic progression of infectious diseases, dividing the population into distinct groups based on their disease status and the population. I will pass it on to Brian to continue. Good morning, everyone. It's a pleasure to be here today to discuss the evolution of epidemic modeling, a field that has significantly advanced our understanding of how diseases spread. The origins of epidemic modeling can be traced back to the 18th century with the pioneering work of Daniel Bennell, who modeled the impact of smallpox inoculation. His work laid the foundation for considering how interventions could reduce the burden of infectious disease on the population. As we moved into the early 20th century, the field began to gain more structure, particularly with the contributions of Ronald Ross, who developed models for malaria transmission. Ross' work was crucial in highlighting the role of vectors and the importance of understanding disease dynamics in the population. In 1927, Kermack and McKendrick introduced the foundational SIR, Susceptible Infected Recovered model, which has since become a cornerstone in epidemic modeling. This model provided a framework to understand the basic progress of infectious diseases, dividing a population into distinct groups based on their disease status. I'll pass it on to Brian to take over.
All right. Thank you, Bill. So this slide, you can see outlines core concept in discrete probability. That is essential for understanding mathematical foundations of epidemic modeling. So we are going to have a closer look on them. So the first point we have is the sample space. So it's a complete set of all possible outcomes in a given scenario. So let's give this example. In an epidemic, the sample space could represent all possible states of individuals in the population. For example, those who are susceptible to the disease, infected or recovered. Next on the slide is the event. So the event is a specific subset of the sample space representing one or more possible outcomes. For example, the event might be that a randomly chosen individual can be infected. We also have the probability of an event. So that's a numerical value between 0 and 1 that quantifies that the likelihood of an event. And in the epidemic modeling, this might represent the probability of disease transmission during the contact. And finally, we have mutually exclusive events. So these events are events that cannot occur simultaneously or at the same time. For example, in a single time step, an individual can simultaneously transition from being susceptible to infected and recovered. So please move on to the next slide, slide 4. So this slide also introduces the foundational framework for epidemic modeling using discrete probability concepts. So we have the successful, denoted by the symbol S. So they represent individuals who have not yet contracted the disease. but even though they have not contracted the disease, they are also at risk. We have the infected individuals, denoted by the symbol I. They refer to individuals who are currently having the disease and can also spread the disease to others. Finally, we have recovered, um, denoted by the symbol R. They include individuals who have recovered from diseases and have assumed to have immunity. So basically, these compartments from the basis of these models, including the SRR models, transition probabilities between these states are often determined using discrete probability distribution. So they provide a structured way to simulate the dynamics of an epidemic model. So I'll pass it on to Buchanan to dilate on the next slides.
Okay, so here we have the discrete probability models in action, and these models help us to forecast some of the ways to control the disease spread and then also make informed decisions. So over here we have the discrete time models where in this case we are able to use time frames to determine the trend in the disease, how it is moving, how it is infecting people, or how the people are recovering within a particular time frame. And then we have the discrete event simulation. So this with this simulation, we consider the events that take place during that time frame and see how they affect the rate at which the disease spread. For example, if someone is infected and then takes a bus to maybe, let's say, Accra, you check those events and see if the reason for the disease spreading is he taking the bus or the environment he was exposed to whilst taking the bus or whatever events that take place during that time frame. And then also we have the stochastic models. In this model, we account for randomness. So we don't look at just one event. We take into consideration other events, and then also with most epidemic, normally when the virus takes some time, it begins to mutate. So we take into consideration this randomness in modeling this stochastic models. Next slide. And then, so these are some of the distributions that we use in these models. So we have the binomial distribution where we have a fixed number of individuals, and then we calculate the number of people who are going to be infected when there is an outbreak of a particular epidemic within that community or within that fixed group of people. And then we have the Poisson distribution where we have fixed interval or space, and then for within that time frame, any event that takes place, we take into consideration how it affects the spread of the disease. So let's take, for example, when there's an outbreak of a flu epidemic, there are maybe 100 people who visit the hospital in a particular day. So having this kind of um, uh, having this kind of idea, it helps policymakers take decisions and then look for policies that will help reduce the rate at which the disease spread. And if let's say the example I was given where 100 people visit the hospital in a particular day, we are able to the policymakers are able to maybe build more hospitals or create more rooms where we are able to accommodate that 100 people in a particular day. And then we have the geometric distribution where we take into consideration the events that took place before the first infection in a particular region. So normally this one is using the SEER model where we have an exposed model, and we look at the number of people that were exposed and the events that took place before one person was infected. So an example is when the COVID, during the COVID era, when the epidemic came to Africa, it took some time before it started infecting people, and they were able to model it and see the rate at which the disease will spread throughout Africa. So, I pass it on to Joel to take next slide.
I'm ready. So I'll be talking about the types of models. We have the SRI model. The SRI model tracks the flow of individuals through three compartments. We have susceptible, which is the people who can catch the disease. We also have the infected, which are the people who have the disease and can spread it. And then we also have the recovered, which are the people who have recovered and are immune. The second model is the SEIR model, which is extended by adding an exposed compartment, which represents individuals who are infected but not yet symptomatic or contagious. The third one is the vector-borne compartmental model, which focuses on diseases transmitted by vectors, including mosquitoes and ticks, and also considers how the disease spreads from vectors to humans. Then again, we have the spatial models, which analyzes how disease spread geographically, and factors including population density, movement, and spatial distribution of cases. Next slide. Challenges. So I'll be talking about the types of models. We have the SRI model. I'm ready. So I'm ready. So I'll be talking about the types of models. We have the SRI model. The SRI model tracks the flow of individuals through three compartments. We have susceptible, which is the people who can catch the disease. We also have the infected, which are the people who have the disease and can spread it. And then we also have the recovered, which are the people who have recovered and are immune. The second model is the SEIR model, which is extended by adding an exposed compartment, which represents individuals who are infected but not yet symptomatic or contagious. The third one is the vector-borne compartmental model, which focuses on diseases transmitted by vectors, including mosquitoes and ticks, and also considers how the disease spreads from vectors to humans. Then again, we have the spatial models, which analyzes how disease spread geographically, and factors including population density, movement, and spatial distribution of cases. Next slide. Challenges and future directions. Equilibrium and stability of endemic status. It's hard to understand how diseases settle in a steady state in real-world situations, especially in populations with different age groups or slow changes. More advanced models that look at both slow and fast changes might help. Modeling multi-strain infections and superinfections. Simple models don't capture the complex ways different strains of how a disease interacts. To understand these interactions better, we need more flexible models. Limits of deterministic models. Deterministic models don't work well in small populations where random events are more useful in real-world situations. Now, I'll talk scalability and computational efficiency. With this, we develop models that can handle vast data sets and complex scenarios in a timely manner, as crucial for real-world applications. Secondly, we have incorporating to create more geographical specific predictions. Finally, we have the advancements in AI and machine learning for improved prediction and for faster processing of large amounts of data. So, in conclusion, discrete probability is essential in epidemic modeling for analyzing and predicting the spread of diseases. It also helps in modeling infection transmission recovery and intervention outcomes using distributions like binomial or Poisson. This approach captures randomness and makes it ideal for small populations or early outstage outbreaks. Stochastic models also enhance realism and provide insights for effective containment strategies, which will aid in better understanding and management of epidemics. Thank you very much.
Thank you.